In this lecture, we're going to talk about transverse shearing stresses in beams. Previously in the semester, we came up with a formula for the average shearing stress. Tau is equal to the shear force divided by the area in shear. And at that time, we said that later on, we're going to learn about a more sophisticated formula. Now, this is it. And I think this is probably the most complicated formula that we have in mechanics and materials. Most of our formulas in this class contain 2 or 3 terms. This one contains 4 terms. And the way that we're going to be able to learn what all those different terms are is by going through the derivation of this formula. So let's review a little bit about what we know about beams. Here's a simply supported beam. It has some different loads on it. There's a triangular distributed load, a point force, and a point moment. And our x-axis goes down the axial direction of the beam. If I want, I can take a free body cut out of a section of this beam, and I'm going to do this kind of in the middle here. I'm going to draw this off to the side. And on that free body section, I'll call that distance delta x, I have some shear forces and bending moments that are internal to the beam that I'll draw in their positive directions. Just a reminder, a positive direction for a bending moment puts the top of the beam in compression. So those arrows go that way. You can see it pulling out from the bottom and pushing into the top. And a positive shearing force goes down if you on the right side of a cut, and it goes up on the left side. So there's my shear force V. Try to make that look like a capital V. And here's my bending moment M. Let's look at a little spot on the side of this beam. I'll draw a little square. That's a stress block or a stress element. And I know from last time how to calculate the axial, flexural, or bending stress in the beam. I use the formula sigma is equal to my over I for the magnitude of the shearing stress. If that is up on the top of the beam, the way I'm going to write that then with our coordinate system starting at the neutral axis is my sigma, and the x direction is equal to minus my over I, where I've got some neutral axis in here, and y is positive up from the neutral axis. Now the transverse shearing stress, what I mean by transverse is the transverse direction is perpendicular to the axis of the beam. The transverse shearing stress will act on the cross section of the beam. This is a side view, if you can imagine looking through the end view, and it will act in the direction that the shear force points on that side of the block. So if you notice the shear force is pointing down on this side, the shearing stress will go in that direction. On the left side, the arrow is going up, and the shearing stress will go up on that side. One of the things that we know about stresses, though, shearing stresses in particular, is that shearing stresses always act as a set. And in addition to those two going up and down, we're going to have 2 shearing stress components that go left and right, and they're all going to be equal to each other. Now, if the x-axis is down the axis of the beam and the y-axis is up in the transverse direction, then the magnitude of the shearing stress we would call tau xy. Now, like I said, we know one way that we can calculate tau xy, and that's based on an average shearing stress. So if I were to look at a side view of this beam and sketch the average shearing stress distribution, we know that the average shearing stress is a uniform stress distribution. That shear stress distribution would go down here, and that would be equal to V divided by the area of the cross section. Now it turns out that this is not a very good way to calculate shearing stress for a beam. And the reason why is if we look at the corners of the beam, up in this corner and up in this corner, although we have shearing stress that goes down, there is no stress on the free surface of the beam. Unless you put some sort of frictional sliding force on it or something, we won't have any shearing stress because there's no two surfaces up here that want to slide past one another. So that means at this corner on the top and this corner on the bottom, the actual shear stress distribution has to go to 0. Let me put that in a red color. Now, if the actual shear stress distribution goes to 0, and the volume of the stress distribution has to be equal to V, the shear force, so we know that about resultant forces, they're the volume of the stress distribution, then the maximum transverse shearing stress has to be higher than the average. Now I'm going to draw this over here, and it turns out, and we'll see this in a little bit, that we get kind of a parabolic shape that goes to that maximum. All right, since V is equal to the integral over the cross-sectional area of tau dA, in terms of the average shearing stress, it's tau average times the area of the cross-section. But in terms of the actual shearing stress, let me put this in the red color. Even though that volume is the same, we don't know exactly what that shape is yet. But we do know if it goes to 0 on the top and the bottom, in order to make up for this cutoff area on the blue rectangle, or the maximum is going to have to be higher than the average. So let's write it this way: tau xy maximum has to be greater than tau average. So we do want to find a little bit better way then of finding this transverse shearing stress. And that's what we're going to do in this lecture. Now the key to finding this formula, before I leave this page, the key to finding this formula is to take a look at the horizontal shearing stresses. Since the horizontal shearing stresses are the same as the vertical shearing stresses, and it's the vertical shearing stress that we think of when we think of the transverse shearing stress, that's what we want. We're first going to find the horizontal shearing stress and then set that equal to the vertical shearing stress on this little green block that I have. That horizontal shearing stress causes a horizontal shearing force in the beam. Let me sketch another picture and then we'll get a little bit more into developing this formula for the transverse shearing stress. All right, so the horizontal shearing stress makes a horizontal shear force. We're going to investigate that. We're going to take a look at our free body section again. And we said that the length was delta x. And we're going to be a little bit more careful about how we label our shear forces on this block. On the left side of the block, so we have our coordinate system that starts somewhere over here. The distance to the left side is x. And so on the left side of this block, we have a shear force that goes up that's V of position x. Over on the right side of the block, it's position x plus delta x. And we have a shear force on that side that is V of that position, V of x plus delta x. And it goes downward. Likewise, we have bending moments on the top, on the left side, m of x, and on the right side, m of x plus delta x. Let's draw a cross-section of this beam, and I'm going to draw this with a little bit unusual shape. I'm going to draw it with a trapezoid shape. We could use any shape. It's going to be a little bit easier if it's a shape like this than some general shape. But I don't want to draw it like a circle or a rectangle because I want to show this formula works for all different shapes of cross sections. So this will be my cross section. Let me label that. So this is on the side view and this is on the end view of the beam. Somewhere here there is a centroid is kind of shifted toward the bottom. I'll exaggerate that a little bit. And associated with that centroid is a neutral axis that we would see over on the side view of the beam. The bending stress distribution, we know what that would look like, so let's draw that picture here down below. On the side view, we know that the bending stress is vary linearly with distance from the neutral axis. The way that bending moment is pointing, we'd have compression on the top and tension on the bottom. The magnitude of the stress on the top would be higher than the magnitude of the stress on the bottom because there's more distance from the neutral axis to the top. Likewise, on the left side, we have tension on the bottom and compression on the top again. But the values of the stress are a little bit different. The value of the stress up here would be m of x times y over I. The value of the stress over on this side would be m of x plus delta x times y over I. All right, so that's what the bending stress distribution looks like. Now, if there's a change in shear force, if there's a non-zero shear force in our beam along that distance delta x, we're going to have a change in bending moment from the left to the right side. In general, the bending moment on the left side and on the right side, m of x and m of x plus delta x, are not going to be the same. So this picture right now isn't in equilibrium. This is not a free body diagram. What I'm going to do is I'm going to draw another picture where I cut off the top part of this figure. I'm going to draw another free body diagram. We haven't done this very often, but we're going to make kind of a small free body cut from a free body cut. I'm going to draw that over here. Where that red line is where I'm making my cut. And I want to show the stress distributions on the left and the right side. Now we're not to the neutral axis, so there is some stress right on that red line. Okay, so the stress distribution makes kind of a trapezoid shape. There's a resultant force from that portion of this stress distribution. That resultant force I'm going to call on the left side F sub L, and over here on the right side I'm going to call that resultant force F sub R. And I'll show you how to calculate that resultant force in a moment. But the point is, in general, the force on the left is not equal to the force on the right because the stresses are different on the left side and the right side. Those bending stresses are different. So in order to keep this in equilibrium, I'm going to have to throw something else in here. I'm going to have another force that acts on this section of free body diagram, which I am going to call delta H. Now if I do the summation of forces in the x direction, I'm going to have FL minus FR plus delta H equal to 0. If I solve for delta H, that horizontal force is going to be the force on the right minus the force on the left. All right, now let's get into the details of figuring out what the force on the left and the force on the right are. I'm going to leave a couple of these pictures on here and move them around, but then we'll start with mostly a fresh page. Okay, there it is, just a little bit smaller and moved around. Now, if you remember, again, the resultant force is the volume of the stress distribution. In this case, the resultant bending force on this piece of the free body diagram of the beam is going to be the volume of that shape. It's kind of a cut-off wedge shape. It's a trapezoid on the side view, but it goes through the thickness of the beam. In order to find this, we're going to do an integral, and the force on the left, F sub L, then is going to be an integral over some area, we'll specify it in just a moment, of that bending stress, sigma x dA on the left side. The area that I'm talking about on the side view is from this red line up to the top, but on the cross section is where we can really visualize the area. Here's that red line on the cross section. I'm going to shade it in. It's from that up to the top, and I'm going to call that A prime. Let me fix that. Oops. That area is A prime. So I'm going to emphasize that with this red color. I'm doing that integral over A prime. Now we know a little bit about the stress distribution on the left side. Sigma x is equal to m of x on the left side times y over I. It points in that direction, so I'm not including the negative sign in this case. And I'll switch to the red. It's over that area A prime. And we can write a similar equation on the right side. The force on the right side is going to be an integral of sigma x dA over that same area, A prime. But now we're using the moment, m of x plus delta x. Oops, and that should be a dA. Let me fix that. Now some things are constant. They don't depend on the cross-section dimensions. The things that do not depend on the cross-section can be taken out in front of the integral. So one more time, I'm going to rewrite these integrals with the m of x over I taken out. We have left a y dA, and over here, an m of x plus delta x over I taken out. And we have an integral again of y dA, and both of those integrals are over that same shaded area, what I'm calling right now A prime. If we look at that integral, we've actually seen that before. An integral over an area of y dA is the first moment of area. We call that the symbol Q. Now we have to be a little bit careful now. Previously we talked about the area of an entire cross-section, and that helped us calculate the centroids of the cross-section. But now we're only talking about the area A prime. From here, where that horizontal force is, that's where I'm going to calculate the shearing stress, and that horizontal force up to the top of the cross-section. We actually don't have to do an integral. We can replace this with y bar A of the shaded area. And that shaded area is in red right there. Now what I mean by y bar A of the shaded area, the y bar goes from the centroid of the cross-section to the centroid of that shaded area. And then the A is the same as that A prime that I just drew in. So if we look at both of these, we can replace this with Q. Let's do that one more time. Force on the left now, I'm going to write as m of x over I times Q, which is meaning to be the shaded area's Q. And the force on the right is equal to m of x plus delta x times I over Q. Now that we know what those forces are, we can go back and take a look at delta H again. We said here that delta H was the difference between the force on the right and the force on the left. Let's write that again. We have m of x plus delta x times I times this q minus m of x times this q and I again. The q and I are common, so I am going to rewrite this one last time. I'm going to pull the q and the I out in front, and we have m of x plus delta x minus m of x multiplied by that q and I. All right, I'm going to try to draw a kind of a 3D perspective picture now on what this force delta H is, and show you now that we have the ability to calculate the shearing stress that goes horizontally in the beam in the same direction as that delta H. Okay, so there's my attempt at trying to draw that shape in 3D. And I'm drawing from that red line up to the top. Okay, so it's from this portion up to the top of the beam. Like I said, it has a kind of a trapezoid shape, so we're cutting off the top of this trapezoid shape and redrawing it here. And this red area I'm trying to show is this surface on which delta H is acting. So if I draw it like this delta H is lying in the plane of this red section. Now the length of this section we said was delta x, and let's call this dimension T. That's the thickness of the beam at where I'm going to calculate the stress at. So if I go up here, this would be the dimension T. Now if we notice, the dimension T can change from the top to the bottom of the cross section. That's allowed. Let's write down what our force delta H is again. We said it was Q over I multiplied by m of x plus delta x minus m of x, like that. And so the horizontal shearing stress, we'll call that item 2, it's nothing more than this force delta H divided by the area on which it is acting, which is the thickness in delta x. Okay, that horizontal shearing stress, it goes horizontal, but we also know now that shearing stresses at right angles are equal. So the shearing stress that goes up and down on the beam cross section, like that, at that spot, is equal to the horizontal shearing stress. So tau, let me label this as transverse, equal to the horizontal shearing stress, is equal to delta H divided by T in delta X. Let's put in what delta H is. It's Q over I. Then we have the T. Then we have this stuff over here, m of x plus delta x minus m of x divided by that distance delta x. Now if we take the limit as delta x goes to 0, so we're going to shrink this down to nothing, then we can get the stress at a point. And we would have this tau is equal to Q over IT, the derivative now of the bending moment with respect to horizontal position x. We know something about this, though. We know that the derivative of the bending moment with respect to x is nothing more than the shear force in the beam. And the way this is usually written is tau is equal to VQ over IT. I will guarantee you will use this equation on your next exam. And what we're going to do is we're going to make sure we understand what all those different terms mean in that formula. And then we're going to do some examples. Okay, so tau is equal to VQ over IT. V is the shear force in the beam. We get that from a free body diagram, or we get that from a shear force and bending moment diagram at a particular position along the length of the beam. So that can depend on X. If you want the biggest transverse shearing stress, then you would look for the place where the biggest shear force is at. I in that formula, if you remember where that formula came from, tau is equal to VQ over IT. The I comes from my over I. It comes from the bending stress distribution. This I is the exact same I as in my over I. It's the moment of inertia of the cross-section, the entire cross-section, about a horizontal line that goes through its centroid. So let's make a note of this. That's the same as in sigma is equal to my over I. That's where it came from. T is the thickness of the cross-section where you want to calculate your stresses at. Now we saw in that trapezoid shape that the thickness changed from the top to the bottom. Sometimes it's constant if you have a rectangle, sometimes it changes. So the way I'm going to write this is thickness of the cross-section at the point of interest, meaning the place we want to calculate the shearing stress at. And the complicated term is Q. Let me write it down, then we'll talk about it and how to find it. It's the first moment of area of the shaded region. It came about through an integral, but we don't have to use an integral for simple shapes, the kind that I'm going to give you. We can calculate it from y bar A of a shaded region. The shaded region is from our point of interest to the top of the cross-section. And the y-bar is from the centroid of the cross-section to the centroid of the shaded area. All right, so there's a lot of terms in there. It can be a little complicated, but with some practice, you'll get the hang of it. So next, let's take a look at some basic examples, and then we'll kind of work our way up and make them a little bit more complicated. All right, so we're going to start out looking at a beam that's simply supported. It's got 1,000 pounds, and the 1,000 pounds is offset, so it's a little bit more to the right side of the beam. I haven't gone through the statics, but I did that on my own. And the reactions on this beam are 250 pounds on the left support and 750 pounds on the right support. So if we were to sketch the shear force diagram in pounds, we would jump up to 250. We would hold constant. We would decrease by 1,000. And then we would hold constant at minus 750. And then we would go up and close that out. That's supposed to be a horizontal line here. All right. Let's have a cross section. Let's just make up a cross section. We'll keep it simple. We'll use the same V diagram for a different cross section later. Let's just look at a simple rectangular cross section. And let's make this 10 inches tall and 2 inches wide. We need to find the centroid of this cross-section. Right in the middle, no problem. We need to find the moment of inertia. Moment of inertia is 1/12 the base times the height cubed. Units on that are inches to the fourth. We're going to apply our formula. Tau is equal to VQ over IT. Okay, so we already found our I. We need to decide where we want to find the V at. Let's see. Let's do the V over at X equal to 18 inches. So we'll be over here. The magnitude of the V at 18 inches is going to be 750 pounds. So we're going to use our formula. Tau is equal to 750. Oops. Got a little bit ahead of myself. 750 divided by my I. And the thickness of the cross-section, well, first we better decide where we want to calculate the stresses at. Let's say we want to calculate our shearing stresses 2 inches from the top of the beam. So this dimension would be 2 inches. And here's my shearing stress on that side. So my T is going to be 2 inches. The T is the thickness. Oops. I have to put that in blue. The T is the thickness. It's not the 2 that I just drew in with the red. It's the blue 2 inches. This dimension, this direction, is the thickness direction. In fact, in this problem, it's a constant 2 inches because it's a rectangular cross-section. Now here's the tricky part, finding the Q. Q is equal to Y bar A, and I'm going to shade in from my point of interest to the top of the cross-section. If I didn't put a Y bar on the previous page, I should have. All right, now the Y bar is the distance from the centroid of the cross-section to the centroid of the shaded area. We got to figure this out. Now from here to the centroid is 5 inches. So the whole thing's 10 inches tall. The centroid lies 1 inch from the top of the beam because it's in the middle of the 2-inch shaded area. So that means the distance from the centroid to the centroid of the shaded area, that Y bar that I need, that's going to be 4 inches. So the Y bar is going to be 4, and the area that I just shaded in is 2 tall and 2 wide. So what goes in here for Q is going to be 4 times 2 times 2. We put all those numbers together and we have our transverse shearing stress at 2 inches from the top. Let's do this again with another location. Let me make a little bit of room and I'll erase my free body diagrams, my V diagram. Everything will be the same except for the location I'm going to calculate my shearing stresses at up and down on the beam cross section. All right, let's calculate the transverse shearing stress at the location of the centroid. All right, so we're going to apply tau is equal to VQ over IT. I'll leave that stuff over there on the right so we can see how that's a little bit different and what is the same. We'll use the same 750 pounds, the same I. The I stays the same moment of inertia of the entire cross-section. The thickness is the same. It's still 2 inches across from here to here. Now what does change is the Q. The Q is what I'm going to shade from the point of interest to the top of the cross-section. It goes all the way up to the top. The area of that now is 2 times 5 It's 5 inches from the centroid to the top, and the y bar is going to be the distance from the centroid of the cross section to the centroid of the shaded area. In this case, it's 2.5 inches. All right. If we wanted a line point of interest below the centroid, then we can still shade in from the point of interest to the top of the cross section and find the y bar. Now, as we get closer and closer to the centroid, you'll notice that the y bar distance gets smaller, but the area gets larger. If the thickness stays constant, the maximum transverse shearing stress would be at the centroid of the cross section. If the thickness decreases or changes, we may have to do some additional calculations to check a couple spots, and I'll show you an example of that in another moment. Let's do another location. Let's do the location at the top of the cross section. We're going to apply tau is equal to VQ over IT. Now, since V and I and T are constant, I'm just going to leave those as symbols. They're the same as what we've already written down before. And let's take a look at the Q. So I shade in from my point of interest to the top of the cross section. Well, look, I don't have any area at the top of the cross section. I could say my y bar distance is 5 inches, but that area is 0. So what that tells me, at the top of the beam, I have 0 transverse shearing stress. That makes sense because we said at the beginning it had to be that way. Let's do one more. Let's look at the bottom. We know that the shearing stress on the bottom of the cross section has to be 0 as well. Let's see why that works out that way with our formula. So if this is my point of interest down at the bottom of the cross section, then I would shade in from my point of interest to the top of the cross section. Okay, tau is equal to V over IT times that Q. Q, the area, is going to be the entire, let me do it in red, it's going to be the entire 10 inches by 2 inches. But the y bar distance is the distance from the centroid of the cross section to the centroid of the shaded area. That y bar distance is going to be 0. So again, on the bottom of the beam, it works out to be 0 for our transverse shearing stress. Now there's a little trick that I'll show you about how you can simplify your Q calculation, but I'll show you that in a few moments. All right, so we did rectangular cross sections. Let's take a look at a circular cross section. We're going to apply our formula. Tau is equal to VQ over IT. And I just drew a circular cross section with a 1,000-pound force. It's a 2-inch diameter bar, so I can automatically write down, here's my 1,000 for my V. My I for a circle is pi over 64, diameter to the 4th power. And now the next thing I need to do is figure out where I can calculate my shearing stresses at. You can calculate your shearing stress at any level in this circle. However, you're going to have to use an integral unless it's at the centroid line. In my class in AEM 250, I'm not going to give you a place on a circle that's different than the centroid of the cross section or the top of the cross section. At the top, we know the shearing stress is 0. Let's calculate what it is here when our point of interest is a line that goes through the centroid. In that case, we would shade in from our point of interest, that line, up to the top of the cross section. And the area we have now is the area of a semicircle. The area of a semicircle is 1/2 pi r squared. And now we need the distance y bar, which is the distance from the centroid of the cross section to the centroid of that semicircle. I don't expect anybody to know this off the top of their head, and I will give you this formula on a test if we have it, if we need it. But it turns out the y bar for a semicircle is 4r over 3 pi. So in this case, the Q would be y bar A would be 4r over 3 pi, where r is a 1-inch radius. Okay. At other places, you'd have to use an integral. However, on the top and on the bottom of the cross-section, we do know that it goes to 0. All right, let's look at another example. Okay, in this example, our cross-section looks a little bit more complicated. It's this plus-shaped cross-section. The dimensions are given 3 inches wide, and it's going to be 4 inches tall. We're going to apply our formula. Tau is equal to VQ over IT, and in this case, I want us to figure out what the value and location of the maximum transverse shearing stress is. First thing we need to do is find our centroid. We already know that the shear force in this case is 1,000 pounds. That might have come from a shear force diagram. Centroid, since this is a symmetric cross-section, is right in the middle. And now we need to find the I about the centroid. We're going to have to use the parallel axis theorem. Let's see, I'm going to break this up into 3 pieces. 1/12 for the top piece, the base times the height cubed, plus the area times the distance from the centroid of the cross-section to the centroid of that spot squared. Now let's see, it's 1 inch from the centroid to this edge and 1/2 inch up here, so this would be 1.5 squared. The central region, 1/12 the base times the height cubed. And there's 0 distance, so there's no parallel axis contribution. And then the bottom rectangle, 1/12 the base times the height cubed, looks just like the top one, plus the AD squared. And for this, I end up with 6.67 inches to the 4th power. Tau is equal to VQ over IT. Now we found V and we found I. We're going to have to figure out Q and T. Now there's a couple possibilities for where the maximum transverse shearing stress could be. One possibility, let me put it in a red color, is through the centroid. Obviously we have the most Q area when we take our line about the centroid. So let's do that calculation. Line that goes through the centroid, let's see, we said 1,000 for V, 6.67 for I. The thickness of this cross-section at that spot is 3 inches. The Q, all right, now here's one little trick to finding the Q for complicated sections. I don't need to find the overall Y bar and multiply it by the overall area for that red region that I just shaded in. The Q is going to be the summation of each piece's Y bar I, A, I. So my Q in this case is going to be the area 1 by 1, the distance from the centroid to here, which is 1.5 inches, plus this region right here, the area is 3 by 1, and the distance from the centroid of the overall cross-section and the centroid of that piece that goes to the junction is going to be 1/2 inch. All right. Let's see what kind of number we get for that. Okay, in this case I get 149.9 psi, effectively 150. But there's another place on this cross-section we need to check. Since this cross-section gets thinner as it goes to the top, it might work out that this location and this location might have the maximum transverse shearing stress. Now remember I said that you shade in from the point of interest to the top of the cross-section. Well, you can also shade in from your point of interest to the bottom of the cross-section. Because we're referencing everything to the centroid, that Q area will be the same whether you shade in from the point of interest at the top or the point of interest to the bottom of the cross-section. So just to have a little bit cleaner picture, I'm going to use this green color, and I'm shading in from this point of interest to the bottom of the cross-section. That would give me the exact same Q in value of shearing stress as if I shaded in from this top junction to the top of the cross-section. So let's call this tau junction. Now it's the same V, it's the same I. The T is different now though. T is going to be 1 inch. And the Q area is going to be, the area is going to be 1 by 1. And the distance from the centroid of the cross-section to the centroid of that shaded area, that is 1.5. All right, let me see what I get for that. I end up with 225 psi. So in this particular example, this is a little unusual. You have to have a kind of a special cross-section for this to work out. For this particular example, the transverse shearing stress is not maximum at the centroid, but it's maximum a little bit higher than the centroid of the cross-section, but only because the thickness of the cross-section changed. All right, let's talk about one last thing. At the very beginning, we were looking at rectangular cross-sections. So let's kind of get back to that. Here's a side view of a beam. I have some transverse shearing force going down this way. This is not a free body diagram. And we said at the beginning that we could talk about an average shearing stress distribution. And it creates a rectangular region on the side view for tau. But the actual shearing stress distribution is a little bit different. If we have a rectangular cross-section, by doing the calculations for tau is equal to VQ over IT, we'll actually find out that the real stress distribution based on that formula, or I can say the more accurate stress distribution, goes to 0 on the top and the bottom and is parabolically shaped. If it's a rectangular cross-section, the maximum transverse shearing stress will occur at the neutral axis. And that's maximum transverse shearing stress. All right. Like I said, it's kind of a complicated formula, some complicated concepts. Just remember, tau is equal to VQ over IT. V and I are easy. T is usually pretty easy if it's a thickness constant cross-section, or I tell you exactly where to calculate the shearing stress at. Q can be the tricky one. Q is a little tough. Q is equal to Y bar A of a shaded area, where you can shade in from your point of interest on the cross-section to the top, or point of interest of the cross-section to the bottom, point of interest on the cross-section to the bottom of the cross-section to find that Q area.